Welcome to this explainer. When we look up at the sky, it's so easy to just see, well, empty space. But today, we're totally reframing that perspective. We're going to explore Earth's atmosphere not as some big void, but as this incredibly dynamic, layered, and invisible ocean of air that completely surrounds our planet. So let's really think about this for a second. We can survive without food for maybe a few weeks, right? We can even go a couple of days without drinking water if we absolutely had to. But breathing, we literally have to do that every few seconds. We cannot survive even a few minutes without air. And honestly, that single, undeniable fact is exactly why it's so absolutely crucial for us to understand our atmosphere in much greater detail. Here is our flight map for today's journey. First, we'll look at our life-giving envelope. Then we'll break down the recipe for air. Third, we'll take a journey through the layers. And finally, we'll wrap up with the weather connection. Let's get right into it. Part 1. Our life-giving envelope, the invisible ocean. I want you to try and visualize this colorless, odorless mix of gases not just as empty space, but as a real, tangible, physical envelope wrapping tightly around the Earth. It's actually a massive, integral part of the Earth's total mass. It gives us the oxygen we need to survive, provides carbon dioxide for the plants, and really, we only ever feel it when it blows against us as wind. But it is always there, maintaining this delicate balance of life. Now, here is a truly wild fact. 99% of the total mass of this entire atmospheric ocean is heavily crushed into just the bottom 32 kilometers from the Earth's surface. To put that into perspective, 32 kilometers is roughly a quick 30-minute drive down the highway. Think about how massive the Earth is, and yet almost the entire weight of this life-sustaining ocean of air is packed into a remarkably thin shell hugging the ground we walk on. It's incredible. Moving on to part 2, the recipe for air, because it's definitely more than just oxygen. When we take a deep breath, what are we actually inhaling? Well, the atmosphere is this complex mix of gases, water vapor, and dust particles, but the recipe is highly dynamic. Let's look at how it shifts around. So the actual recipe of the air changes drastically the higher up you go. You might think oxygen just extends upwards forever, but actually it reaches an almost negligible quantity by the time you hit an altitude of 120 kilometers. And carbon dioxide and water vapor, you'll only find those up to about 90 kilometers from the surface. The whole mixture is heavily weighted toward the absolute bottom. A truly defining ingredient in this recipe is carbon dioxide. Meteorologically speaking, it's a real game changer. It acts almost exactly like a one-way mirror. It is totally transparent to the incoming solar radiation from the sun, meaning it lets all that heat right in. But it's opaque to the outgoing radiation trying to escape Earth. It absorbs a chunk of that outgoing heat and reflects it right back down to us. This is what we call the greenhouse effect. And as carbon dioxide volumes rise due to burning fossil fuels, this heat-trapping mechanism just keeps turning up the temperature of our air. Water vapor is another super variable ingredient. Down in the warm, wet tropics, water vapor can make up to 4% of the air's volume, but travel to dry, cold deserts or the polar regions, and it drops to less than 1%. It decreases from the equator toward the poles, and it decreases as you go higher in altitude. Just like carbon dioxide, it absorbs heat from the sun and preserves Earth's radiated heat, essentially acting as a variable thermal blanket, keeping our planet from getting dangerously hot or dangerously cold. Which brings us to one of the most fascinating microscopic processes happening right above our heads. Our atmosphere has this massive capacity to hold tiny solid particles. We're talking sea salt, fine soil, smoke, soot, ash, pollen, and yes, even disintegrated bits of meteors. Higher concentrations of this dust are usually found in subtropical and temperate regions, swept up by dry winds. But here is the real magic. Dust and salt act as hygroscopic nuclei. Basically, they are the vital, microscopic seeds that water vapor condenses around to actually create the clouds we see in the sky. All right, Section 3, Journey Through the Layers. We know the ingredients, so let's check out the structure. We're going to launch straight upwards on a vertical climb to see exactly how the density and temperature of the atmosphere shift, and I mean violently shift, layer by layer as we go higher. We know density is highest near the surface and thins out as you climb. But what's really amazing is how the entire column of our atmosphere is broken down into 5 completely distinct layers based entirely on temperature conditions. and the temperature actually zigzags back and forth as you gain altitude. Here is the exact sequence we'll be traversing on our expedition, from the ground up to the absolute edge of space. We kick off in the Troposphere, then move into the Stratosphere, push through the Mesosphere, shoot up into the Ionosphere, and finally bleed out into the Exosphere. Let's do it. We start right here in the Troposphere. This is the lowest layer and honestly the absolute most important one for biological life. It averages about 13 kilometers in height, which means even when you're on a commercial jet at cruising altitude, you are still flying inside this biological zone. Interestingly, it's actually thicker at the equator, reaching about 18 kilometers, because strong convectional currents push heat way up high there. This layer holds the dust and water vapor we just talked about, meaning literally all weather and climate changes happen right here. And as you climb through it, the temperature steadily drops, about 1 degree Celsius for every 165 meters you go up. But brace yourself, because as we hit the ceiling of the troposphere, a boundary known as the tropopause, the temperature over the equator abruptly plummets to a freezing -80 degrees Celsius. Over the poles, it's a bit warmer at -45. The temperature right at this boundary stays pretty much constant, which is exactly why I earned the pause in tropopause. Crossing that boundary, we enter the stratosphere. Extending up to about 50 kilometers, this layer is famous for one absolutely critical feature: the ozone layer. Sitting between 10 and 50 kilometers up, this ozone acts as our planet's indispensable filter. It absorbs the sun's intense, harmful ultraviolet radiation, quite literally shielding all life on Earth from devastating cellular damage. As we push past the stratosphere and enter the mesosphere, which goes all the way up to 80 kilometers, the temperature roller coaster takes another massive plunge. It drops rapidly as we climb, hitting a bitter, bone-chilling -100 degrees Celsius at its upper limit, an area called the mesopause. Shooting past the mesopause, we enter the ionosphere, sitting between 80 and 400 kilometers up. And the rules totally flip here. The temperature actually starts increasing with height again. But the standout feature here? It's filled with electrically charged particles called ions. These ions are incredible because radio waves transmitted from Earth hit this layer and get reflected right back down to us, making long-distance radio communication across the globe possible. Finally, we reach the exosphere. This is the absolute uppermost layer of our atmospheric structure. And honestly, very little is actually known about it. Whatever gaseous contents do exist way up here are extremely rarefied. There is no hard boundary where it just abruptly stops. Instead, this quiet frontier just slowly, gradually fades away, merging entirely with the vastness of outer space. Okay, now that we've touched the very edge of space, let's bring our vertical journey rapidly back down to ground level for part 4, the weather connection. How do these massive atmospheric structures actually connect to our daily human experience? Well, while all the layers influence us in some way, geographers and meteorologists are mostly focused on those first two bottom layers. That bottom section is where we find all the active elements of weather and climate. We're talking temperature, pressure, winds, humidity, clouds, and precipitation. These are the dynamic, constantly shifting variables born from the water vapor, dust, and greenhouse gases that are compressed into that first 32 kilometers. These elements dictate our seasons, our agriculture, and literally our daily lives. So, we've mapped out the recipe. We've charted the dramatic, freezing, and charged layers of this incredible vertical ocean. But it leaves us with a huge thought to ponder. We know the ingredients, and we know the structure. But how exactly do the shifting pressures and temperatures of these invisible layers interact to generate the winds, the intense storms, and the weather we feel on our skin every single day? That is the next great puzzle of our atmosphere, and I really hope this foundation makes you want to look up at the sky and figure out exactly how it all works.